So in this, our third of 3 lectures on the climatology of the tropics, we're going to give our first demonstration that diabatic heating drives tropical circulations. If you take nothing else from this course, take that diabatic heating drives tropical circulations. Big circulations, small circulations, it doesn't matter. Most of our tropical circulations have ties back to diabatic heating. But first, what is diabatic heating and what forms does it take? So that's what I want to start with here, and then we'll look at a very basic demonstration of how diabatic heating can drive tropical circulations. So first, let's introduce this concept called specific enthalpy, or enthalpy per unit mass. So diabatic heating, and we'll use the term heating very generically. When we're talking about warming, we'll say warming, and that will be positive diabatic heating. And when we're talking about cooling, we'll say cooling, negative diabatic heating. But whenever we say diabatic heating, we're not specifically saying that it is warming. It could be warming or cooling depending upon the sign. But diabatic heating is manifest as changes in specific enthalpy, which is defined as the following. So we have specific enthalpy here on the left. Then we have C sub P times T. So the C sub P is the specific heat of air. So there's dry air, there's moist air, there's even liquid water within the air. In this case, we're being very overly simplistic. We're neglecting ice phase stuff, which is okay in most levels of the tropics, especially near the surface. But again, this is just a bit of a simplification. So we have something related to changes in temperature here. Then we have something related to changes in moisture content here. We have the water vapor mixing ratio Q sub V here times the latent heat of vaporization that we see here. So if we're looking at changes in moisture at constant temperature, we're going to change enthalpy through this term here. But if we're looking at changes in temperature, whether or not we're at constant moisture, we're looking at this term that we see here. Again, somewhat simplistic, but more than sufficient for our purposes here. So with that in mind, what are the predominant types of diabatic heating that we are concerned with here in this course? So we have a diagram that a very similar version of this tends to show up in every introductory meteorology textbook, every climatology textbook, because it governs the heat balance within the atmosphere. We have 4 different sets of energy flows that we see here. Our first one, encompassing 2 different types, is radiative heating. So this is changes in enthalpy that result from the net absorption of radiation emitted by the sun, as well as the Earth and the atmosphere. So we're looking at the balance between what comes in and is absorbed versus what is emitted and goes out, away to outer space. So the amount that's coming in from the sun is depicted here by the red box that we see. This is what we call shortwave or short wavelength radiation. And that which is emitted from and comes out from the Earth and its atmosphere is given by the purple box here, what we call long wave, because it is at longer wavelengths. So the net balance between this incoming and outgoing, to some extent short wave versus long wave, but there is also absorption and re-emission within the atmosphere. So it's not exclusively short versus long wave. But amount in and absorbed versus amount out because of its emission is what characterizes our radiative heating. Oftentimes, yes, during the summer and during the day, radiative heating is positive radiative warming. During the nighttime, as well as during winter, especially away from the tropics, we have radiative cooling or negative radiative heating. We also have latent heating here in the dark blue, almost black box that you see here. There are 2 forms that this takes. You can have surface latent heating, which is listed as evapotranspiration. Here in the Midwest, we often hear that term in the context of the cornfields of the Midwest. It's not just off of corn, but it's more generally evaporation and or transpiration from the underlying surface, whether that be land or water. But we also have latent heating within the atmosphere, of which clouds and more generally precipitation are the primary contributors to latent heating. This latent heating characterizes changes in enthalpy resulting from phase changes of water at constant temperature. So latent heating in and of itself is taking vapor and condensing it, taking water and evaporating it, and then when you get into ice phases, you also have freezing, melting, sublimation, and deposition as you go from water to solid and vice versa, or vapor to solid and vice versa. These are all changing the water-vapor mixing ratio and thus changing the enthalpy at constant temperature. However, these processes also do change the temperature themselves. When you are evaporating, when you are melting, when you are sublimating, you require heat input from the surroundings to accomplish that phase change. So you are cooling the air and changing enthalpy in that way as well. Whereas when you are freezing, when you are condensing, or when you are depositing water vapor or water substance, this releases heat to the surroundings as you go to the colder phases. And so consequently, those are all warming processes. So you again get a warming change in temperature associated with this phase change as well. Our last one is sensible heating, given by this yellow box that you see here that is listed as thermal. And that is the primary way in which sensible heating is manifest within the atmosphere. This results typically from heating of the underlying surface, whether that be by radiation or some other process. But you get a temperature difference between the underlying surface and the air that resides just above that. So the heat transfers from whichever surface is warmer to whichever surface is colder. Sometimes that's from the land or water to the air. Other times it's from the air down to the land or to the water. So we have three major types of diabatic heating once again. Radiative heating related to radiation balance, what comes in versus what goes out. Latent heating related to phase changes of water within the atmosphere as well as at the surface. And sensible heating, specifically at the surface, since it requires two different substances to be in contact with each other, like air with the water or land at the ground. So let's consider a few examples. One is very near and dear to us this time of year, cold, dry air passing over the relatively warm Lake Michigan waters in winter. So I'd encourage you to pause for just a second before hearing me describe this to think briefly, what do I expect in terms of the diabatic heating that this implies? So we have two types here. We have a surface sensible heating. The water is relatively warm and the air that passes over it is relatively cold. So there is a transfer of warmth from the warm water to the relatively cold air just above it. So when we get westerly wind blowing across Lake Michigan from Wisconsin toward Michigan, it's usually warmer in Michigan this time of year because of the warmth that it gains from the lake below. There's also surface latent heating. The air is relatively dry and the lake, of course, is moist. It's a lake after all, it's water. So there's surface evaporation that takes place, moistening the air just above the lake's surface. This evaporation requires energy input to accomplish, going from water to vapor. And so this also slightly cools the lake as it accomplishes this evaporation. But what about something more germane to the tropics? Tropical cyclones, tropical storms, and hurricanes. These are fueled by surface enthalpy exchange. This enthalpy exchange implies a diabatic heating process, and surface implies that it's happening at the surface as well, just like we saw in our lake example above. But what does this actually look like? So again, we have a surface sensible heating manifest in terms of surface sensible warming. As air passes just above the water's surface, going in toward lower pressure near toward the center of the storm, it actually cools slightly as it goes up in a pressure sense towards slightly cooler temperatures. So this warm water transfers heat to the air to ensure that it remains relatively warm even as it goes toward lower pressure as it comes in toward the center of the storm. There's also surface latent heating that takes place. You've got subsaturated air flowing in above the wet, water-filled ocean. So again, you have evaporation from the underlying water surface to the air above, causing the air to gain water vapor, gain enthalpy, while the ocean cools slightly due to that evaporation. We can also consider precipitation falling into a subsaturated near-surface layer. We see this a lot with the onset of snow or rain around here, but you can see it in the tropics as well. So you've got liquid or solid water substance in the middle to upper troposphere that is falling down into something that is not fully saturated closer to the surface. Here we have predominantly latent heating. And note that we've taken away the prefix of surface in this case because it's not happening just at the surface. As this precipitation falls, let's assume that it's in liquid form. It's going to evaporate and help to moisten that air. So there's going to be a phase change that leads to an increase in water vapor for that subsaturated air column nearer to the surface. But that evaporation also requires energy input, which will cool the air at the same time. So this gives rise to the idea of evaporative cooling, and we often see this in the wake of thunderstorms, whether in the mid-latitudes or in the tropics. From here, having defined the primary sources of diabatic heating, we can define this idea of heat sources and moisture sinks. So we're going to start with this heat source or an apparent heat source, Q1. We'll define this as vertically integrated. So we're going to consider the entirety of the troposphere, really the entirety of the atmosphere, ignoring the structures that may be present at different levels within the atmosphere. So this apparent heat source, which is a very close proxy for the total diabatic heating vertically integrated within the column, has three components on its right-hand side. The first one is our vertically integrated net radiation. So these brackets here are indicating vertically integrated through the troposphere and above. And this is our radiation, the balance between what is absorbed and what is emitted to space. We also have our precipitation rate here, P, which is defined as condensation minus evaporation. So again, neglecting ice phases, we assume that all of what condenses either evaporates or falls out in the form of precipitation. So this condensation minus evaporation is the amount that is not evaporating and thus must be precipitating out. So this term here is a latent heating term, and this L sub V that we see here is again our latent heat of vaporization. So this is associated with phase changes and increases in enthalpy or decreases in enthalpy associated with those phase changes. Note that this P can actually be negative. Just because we're defining it as precipitation, it may seem like an oxymoron to have negative precipitation. But if evaporation exceeds condensation, this P would actually be negative, and thus the depiction of it as precipitation is perhaps stretching the physical truth ever so slightly. This S term here is related to surface sensible heating, transferring to the atmosphere. When S is positive, you're transferring heat from the ground or water surface to the atmosphere above. When it's negative, you're transferring it from the atmosphere to the ground or water surface below. So in this case, when you have upward sensible heating, gaining heat in the atmosphere, when you have precipitation, and when you have a net absorption of radiation, you would have a net increase in your temperature associated with this positive value for the apparent heat source. Whereas if you had net radiative cooling, sensible heat transfer directed toward the ground or surface, and evaporation exceeding condensation, you would have a negative value for this heat source and thus diabatic cooling. Likewise, we can also define a vertically integrated moisture sink. We'll call this Q2. Because it's vertically integrated, we'll put brackets along it here as well. And this term looks somewhat simpler here, and it's entirely associated with phase changes of water, so a latent heating process. P again is our precipitation rate, condensation minus evaporation. But here it's offset by this E term here, which is related to surface evaporation. So just as S on the previous slide was the surface sensible heat transfer, this E is the surface latent heat transfer. So when you are gaining moisture from the underlying surface into the atmosphere, this E will be positive. When you are losing moisture from the atmosphere to the underlying surface, this E will be negative. Q2 is defined as a moisture sink, and so consequently it is positive for water vapor loss. And so in the case where you are gaining moisture from the underlying surface and E would be positive, assuming that there's no precipitation, you would end up with a negative value for the moisture sink and thus a moisture gain within the atmosphere. Whereas if you are losing moisture to the underlying surface, or if you have more precipitation than you do atmospheric evaporation, more condensation than you have atmospheric evaporation, you are losing moisture, you are losing water vapor more specifically, and thus Q2 would be negative. So from here we can take archived data from models and from satellites to be able to look at how this heat source Q sub 1 and this moisture sink Q sub 2 vary spatially across the tropics and subtropics as well as throughout the year. And this depiction here is for the January through March period, so the southern hemisphere summer times. The bottom panel is outgoing long-wave radiation, which is a measure of how much radiation is being lost from the atmosphere to outer space. When the skies are clear, you have more that is able to escape to space. Whereas if you have clouds, especially thunderstorms, those features trap that outgoing long-wave radiation, at least some measure of it. They absorb it, and then they emit it in all directions, some of which is to outer space, but some of which is back toward the surface as well. So when you have clouds, when you have thunderstorms, outgoing long-wave radiation is typically relatively low, whereas when you have relatively clear skies, it's relatively high. So we can compare Q1, which has radiative, sensible heating, and latent heating components, to Q2, which is only latent heating, to outgoing long-wave radiation, which is strongly controlled by the processes that lead to latent heating, to be able to infer what are the dominant sources of diabatic heating driving the tropical circulations. So what we see here, if we focus on South America, the maritime continent, and along the South Pacific convergence zone, Southern Africa, and into the equatorial Indian Ocean here, we have large values of Q1 in all of these regions. We have large values of Q2 in all of these regions, and we have low values of outgoing long-wave radiation in all of these regions. So we have warming in these regions as implied by the heat source, but we don't yet know if it's radiative, sensible heating, or latent heating driven. We have large Q2, which implies that we have strong latent heating taking place. We have net precipitation falling out, which implies that there is substantial condensation taking place. Condensation can only occur if we have ascending motion lifting a parcel to condensation. This low set of outgoing long-wave radiation through these gray shadings that we see here also implies the presence of clouds and/or thunderstorms. So the combination of large positive Q1, large positive Q2, and low values of outgoing long-wave radiation strongly implies that latent heating is driving the diabatic heating that we're seeing in the heavy precipitation regions of the southern hemisphere during the southern hemisphere summer. Likewise, if we go to northern hemisphere summer, July through September, we see again with the Indian or Asian monsoon, very high values of Q1 extending out into the intertropical convergence zone of the western North Pacific. Same across Central America and into the northern portions of South America, and to lesser extent over Western Africa. The moisture sink is relatively high in these locations as well, and outgoing long-wave radiation is also relatively high in these locations. Again, strongly implying that latent heating is the primary diabatic heating process driving or characterized by these diagrams. Net warming associated with the heat source, but we don't know if it's radiative, sensible, or latent heating driven until we look at Q2, where we see that it's very large, which implies a net precipitation associated with condensation, and the OLR, which is very low, which implies clouds and thunderstorms. So not only is diabatic heating present in these locations in the tropics during the local summer months, but it is also predominantly driven by latent heating. Now that's not to say that sensible heating and radiative heating aren't important in these locations or aren't important in other locations that we have not considered specifically in this interpretation, but that in the places where it is precipitating, where the most significant sensible weather takes place in the tropics, it is primarily latent heating that is driving those outcomes. So then we can ask the question, having talked all about what diabatic heating is, what it means in terms of enthalpy, what forms it takes, and where we tend to see them, can we show that diabatic heating drives tropical circulations? And just like Bob the Builder, yes, we can. We can show that it drives tropical circulations. The jokes don't get better through the course of the semester, I promise. I'm sorry. So what we have depicted here on the left panels here is diabatic heating for 2 months, January 1989 and July 1989. So Southern Hemisphere summer and Northern Hemisphere summer in the top and bottom. This vertically integrated diabatic heating is very analogous to Q1, and they're very similar to the Q1 distributions on the previous 2 slides. Maximized from Africa through the Indian Ocean, across the maritime continent, and across the South Pacific Convergence Zone, as well as South America during January. Then here, portions of Africa and the Middle East, but especially India to Southeast Asia and the Western North Pacific, along Central America in the far eastern North Pacific, and to lesser extent extending over toward Western Africa here. So these are very similar to what we've seen on the previous 2 slides. And now we want to take this information and put it into a simplified atmospheric model, what we call the shallow water equation model, to be able to get an estimate of atmospheric circulations exclusively driven by this diabatic heating. So we're going to start at 850 hectopascals, so close to the surface. And we have an analysis here in the top. So this is a metric of what actually occurred in January 1989. And then here we have the model output on the bottom. So this is what diabatic heating within the simplified atmospheric model would result. Many of the climatological features we introduced in our last video are labeled here. So we have our subtropical highs in the analysis over the ocean here at 850 hectopascals. And we have this monsoonal circulation near Australia and the maritime continent as well, with our easterly trade winds. As we see, the bottom panel very closely resembles the top panel. There are some areas of disagreement. South America is the biggest one here between the analysis and the model output. But by and large, they're very similar. You get oceanic subtropical highs. You get easterly trade winds, especially in the Pacific and Atlantic basins. You get this monsoonal circulation here near Australia and the maritime continent. And even in the northern hemisphere, the features are a pretty good match, despite it being the winter time there. If we go to July, we get the same type of agreement. Subtropical highs over the North Atlantic and North Pacific Ocean in both the analysis and the model output. We get some disagreement here over Mexico, southern portions of North America, where we see a very strong heat low driven by the diabatic heating in the model output that we don't really see nearly as strong in the actual analysis. However, a corresponding feature in the Sahara Desert is reasonably well depicted in both the analysis and the model output. But in particular, we get this cross-equatorial flow coming from the southeast and then spinning around to the southwest and then spiraling cyclonically into this monsoon trough, monsoon circulation over India and Southeast Asia in both the model output as well as the actual analysis. So again, the diabatic heating that we input into this model, a lot of which is driven by latent heating in the precipitating regions, is sufficient to be able to help us understand what these tropical circulations look like, at least at low levels. So simply stated, diabatic heating drives tropical circulations on all scales. We could go in there and show that that also holds true at 200 hectopascals, but we can have a pretty good confidence that if it's matching pretty well near the surface, because everything within the troposphere is intricately linked to each other, it's probably a pretty good match at 200 hectopascals as well. So instead of doing that, we're going to wrap up this lecture and wrap up this video series looking at this distinction between convective and stratiform heating. So to this point, when we've considered diabatic heating, we've looked at vertically integrated quantities over the depth of the atmosphere, or more specifically the troposphere, where most of this is taking place. But there's very rich structure, especially for latent heating, within the vertical. It's not all constant or uniform with height in the vertical direction. So this distinction between convective and stratiform heating helps us to understand the two different types of latent heating profiles that are commonly seen within precipitating features within clouds, not just within the tropics, but also in the mid-latitudes. So here on the left panels, we have our convective heating. This is associated with warming throughout the troposphere, with a maximum here in the middle portion of the troposphere. This is driven by low-level convergence. So we have divergence here at the lower left. Positive values are divergence, negative values are convergence. So we have convergence in the lower portion of the troposphere, so the winds are coming together as depicted by the red arrows, which means they thus must ascend as you go upward from there. And so we have a maximum of ascent in the middle troposphere once you cross over to divergence. That happens to correspond with this maximum value of the diabatic warming in the mid-troposphere. We have upper level divergence, positive values depicted here with the black line. So air coming in, rising throughout the troposphere, and then spreading out near to the tropopause. Stratiform, however, takes on a somewhat different structure, and this is commonly associated with stratiform clouds, whereas convective is generally associated with deep moist convection or thunderstorms. So this is associated with low-level cooling, negative values here, so latent cooling, diabatic cooling, but warming in the middle to upper troposphere here, with zero sort of in the mid-troposphere. In association with this, we see low-level divergence, mid-level convergence, and upper-level divergence once again. So we have air coming together in the mid-troposphere, and it ascends and descends from there, where it diverges near to the surface, as well as in the upper troposphere. We have our maximum warming, where we see ascent. As we might expect, as air is ascending, it is condensing and releasing that latent heating to create that warming. Whereas here with our descent, as precipitation is falling out, a chunk of it is typically evaporating, producing our evaporative cooling, and thus the stratiform cooling beneath heating or warming profile that we see here. So we'll revisit this at a couple of times later on in the semester, but the takeaway from this lecture is that diabatic heating in all of its forms, especially latent heating, which is predominant within the tropics, drives our large-scale tropical circulations. In later lectures, we're going to describe different features of the tropics for which diabatic heating is also intricately linked and/or a driving feature of their circulations. But that's it for our tropical climatology series of videos.